Computer Science and Engineering Industry Affiliates Lecture features the latest information in computer research, development, and education, benefiting business, industry, and academia.
Thank you very much for being here at the CSC Industrial Affiliates meeting. Most of you know me, I'm Hank Levy, I'm chair of CSC. It's my pleasure to introduce Josh Smith, who's an associate professor both in computer science and engineering and electrical engineering. Josh got his bachelor's degree in philosophy and computer science at Williams College. He then did a master's degree in physics at Cambridge University in the UK before doing another master's and PhD at the MIT Media Lab. From 2004 to 2011, he worked at the Intel Seattle Research Lablet, which was over on 45th, and as many of you know, was very closely tied to our department. He joined us in 2011 as the third hire in the Excel program, which was a program to, and is a program, to hire faculty jointly between EE and CSC along the computer engineering boundary. Josh is quite an inventor. In his previous life, he's been responsible for a number of interesting things, from sensor technology that's used in cars to protect young passengers from airbag injuries, to digital watermarking systems for postage stamps, to touch sensors, to robots. And he was very well known for a thing called WISP, which stood for Wireless Sensing and Computing Platform, a little sensor that draws its power from RFID signals. At UW, he's been working on a number of exciting projects along with some of our other faculty, in particular on systems that draw their power out of thin air. Josh.
Thank you very much for that introduction, Hank, and it's a really exciting, great opportunity to be talking to all of you. So I'm going to be talking about powering the Internet of Things, so RF-powered sensing, computing, and communication. I'll start by thanking my students who are both in CSE and EE, and the ones whose names are in red under here are giving talks at various times today, so keep an eye out for them. I also want to thank sponsors, government sponsors, but also a lot of industry sponsors, some of whom are here: Intel, Google, C4C, Washington Research Foundation. So all this work is made possible by you. So, why wireless power? Well, one way to answer it is this. John Chambers recently said, the Internet of Things, I think, will be the biggest leverage point for IT in the next 10 years, 14 trillion in profits from that one concept alone. That's one way to think about it. Another is in terms of the specifics, and it's interesting to think about the specifics because it points to different benefits, some of which come up in different applications. So obviously cords are terrible for all kinds of reasons. I probably don't have to spend too long convincing you of that. Batteries is one way to power things that eliminates cords, but batteries have a number of problems. They run out, then your things die. They're also large, they're heavy. So getting rid of batteries has several different benefits. Another one that I like to talk about is sometimes call it monolithic technology. So that's actually the monolith from 2001: A Space Odyssey. If you look at my phone right now, it's not quite like that. It actually has some buttons and it has various ports for connectors and things. And that is a benefit that wireless power can help with, both for consumer electronics and for biomedical applications. So we'll talk about that a little bit more later. There are also design benefits. I mean, if I add a solar cell to something like this car, well, there's a nice green surface. Well, I had to make it black to put a solar cell on there. Our devices are already designed to pass radio signals. So if we can use that same box, that same form factor, same materials to transfer power as well as signal, that's exciting. Another thing that's related to that is the fact that RF harvesters are built from electronics, as opposed to solar cells or mechanical harvesters, which are really non-electronic things. So you have to get different materials, different fabrication processes. One of the nice things about RF harvesting is it's just a circuit design that you include in your system. Okay, so hopefully I've convinced you that RF power or wireless power would be good, but so would a flying car. Is there any reason to think we can do this now? And the reason that we can start to do this now is captured in this plot here. So if you don't look very carefully, this looks like The Moore's Law curve you've seen many times. We've got decades from 1940 to 2020 across the bottom. The vertical axis in this plot, though, is not number of transistors, but it's energy efficiency. It's the number of instructions we can execute using 1 microjoule of energy. And so the striking thing is that this performance number has improved by a factor of 1 trillion from 1940 to today. And that's why we couldn't have imagined wirelessly powering things 20 years ago, and now it's starting to become possible. So I'm going to take you on a sort of tour of the space of wirelessly powered systems. I like to divide it up on these 2 axes, far field and near field. So far field systems are powered at relatively long range and tend to be sort of low quantities of power. Near field systems can be much higher power but shorter range. And then another axis that's interesting to think about is planted versus wild. So in the planted case, we're transmitting power deliberately with the intention that somebody's going to receive it. In the wild case, we're going to be using power that's already here for some other reason and just capturing it. So I'll talk about several systems in this space. So just to give you a first example, I'll show you WISP, which Hank mentioned, stands for Wireless Identification and Sensing Platform. What you see on the lower right here is an RFID reader. It's emitting radio signals. It's been disguised to look like a picture frame. The stack of boards in my hand was a very early WISP that had an accelerometer on it. And so the little stack of boards there is being powered by the radio signals that the reader's emitting. As I tilt it back and forth, an accelerometer is measuring the tilt with respect to gravity. And then that stack of boards is communicating by reflecting the radio waves back to the reader. So that's called backscatter, which is a very power-efficient way of sending data, because that little board doesn't have to generate its own radio signals. It's just reflecting the radio signals that are emitted by the reader. And so it doesn't have to spend any power to generate those signals. We've been working on that for several years. Most recently, we've created what we call the WISP-5, which has much greater range. So the previous generation had about 4 meters of range. This has something like 9 meters of range, all powered from the same reader. So we're benefiting from that exponential that I showed you before of every few years the process technology is making this more and more energy efficient so we can do more. The other exciting thing is that this one has a new type of non-volatile memory called FRAM, which is like flash, but it's so low in energy. It's, as far as writing to it and reading from it, it's almost as fast and low in energy as RAM. Now, one thing I should tell you about how these power harvesting systems work, because most of them work this way, and this is a question people often ask. The red trace you see there is the harvested energy. So this system is starting up from 0 volts. It accumulates power gradually. And then at a certain point, it has enough to do something. So it's storing energy on a little capacitor. Once it has enough energy accumulated, then it wakes up and does something. And that's the downward slope. Then it goes to sleep, and then it charges up again. So essentially, all energy harvesting systems look something like this. They have an energy store. They have energy coming in at a sort of unknown and variable rate. So it takes a while to accumulate enough energy to do whatever it is that needs to be done. Then they do some work. Then they go back to sleep. So basically, all these energy harvesting systems look something like this. They have a store of energy. They spend time sleeping and waking. And the various ways you decide when to sleep and when to wake determine a lot about how the system works. Now, one question we've been asking recently is, how far can we go with these RF-powered battery-free sensors? So I showed you the accelerometer, which is very simple. There's not a lot of data there. Recently, we've been trying to do more and more aggressive, sort of bigger things. What I'll show you here is a battery-free microphone. So microphone is typically tens of kilohertz. It's many more samples than what I showed you in the accelerometer example. This was inspired by a bug that the Soviets actually created quite a while ago. It was a battery-free listening device that was put into the American embassy. It stayed there for 7 years. And we're doing something similar, but we have digital control over it. So I'm actually going to play you audio that was captured at a distance of about 7 meters with a completely battery-free microphone. Find my mouse again so I can play this. So it's fairly noisy because it is at long range. At closer range, it's you know,
here's something we
much clearer. But for us, this is a big step forward because we're dealing with a high data rate signal now, not just a sensor that we pick up once in a while. Now, this is a very new result that I'm excited about. My student Saman Naderi-Parisi has just done this, and he's going to be giving a talk about this today. So we've actually built a battery-free, wirelessly powered camera. Now, this isn't taking, you know, full frame rate video, of course, because you're very power constrained, but this can take, you know, one picture every 20 seconds at about a meter from the reader, or one picture every 3.5 minutes from 4 meters away. And so that's enough for many interesting applications, things like, you know, surveillance, inspection, things like that. The images you see along the bottom are showing what happens as you allocate different amounts of energy to different pictures. So the picture on the left is sort of not enough energy. The camera's really not working here. Over here, we've allowed it to spend more time collecting light, and you have a better quality image. Here are some other, you know, better quality examples that we took from around the lab. We took a picture of the robot here. We've got the Husky logo and a Rubik's Cube. And the interesting thing actually about the Husky and the Rubik's Cube is those were actually taken through the wall. So we put the tag in one room, we put the reader in the next room, and read it through the wall, which is, you know, one of the neat things you can do with wireless power. So you could also imagine putting those cameras inside a wall with something that had a little flash to generate some light. So we think this concept of the battery-free wireless camera is really exciting. And it's you know, much more ambitious in terms of data than what we were doing with, say, the accelerometer. But again, to make this happen, the system has to sit there accumulating power for a while, and then it can take the picture and backscatter the data. Okay, so next, I'm going to tell you about a system that is also far field, but we call this wild power, meaning it's ambient signals. What we realized is that if you're several kilometers from a TV tower, you're getting about the same amount of power as if you're 10 feet from an RFID reader. Now, one of the challenges for all of these systems is unless you have enough signal, the power harvester can't turn on at all. So the inner circle that you see here is the range we were able to get several years ago. Then recently we've come up with a newer harvester design that allowed us to move out, you know, to much further away, you know, beyond 20 kilometers from a 1 megawatt TV tower. Now, another challenge we've been working on recently is what I'm going to tell you about now. So the blue traces there is essentially the TV spectrum. So each spike that you see is like one TV channel. And the little sort of parabola you see there is the energy we're able to harvest, the frequency band over which one of our harvesters is designed to work. So typically we have to pick a TV station and tune the harvester to work on that station. But obviously there's a lot of other power out there, and when I go from place to place, the mix of frequencies is going to be different. So with multiband harvesting, we have a way to harvest from a bunch of different frequencies next to each other, and that allows us to work with different mixes of frequencies. So if we take the demo down to California, there'll be different set of TV stations. We can work with those. And the other nice thing is that we get power from multiple sources at once, so we get more power. And the way we've done that is basically to build several power harvesters, each narrow band, each tuned to a specific frequency, but all connected to one wideband antenna. And so this is a picture of a 5-band harvester. You can see that kind of structure there. So we're excited about this as one of the ways to make ambient RF harvesting more practical. Now I'll tell you about a project that I did with Sham Golakota, who's running a session today where some of this is going to be talked about. So we can power these devices from TV signals, but you know, now what? You know, what are they going to talk to? It turns out we can do something similar to what I showed you with the Saturn video, where the tag was talking to the reader by reflecting radio signals. Turns out we can reflect ambient radio signals, not just get power from them. So if we have these two ABC tags here harvesting power from the TV tower, they can actually send messages to one another by reflecting that ambient TV signal. So I'll show you a video here illustrating that. So this is a couple of miles north of here. These two devices are being powered by the TV tower. Now this is a powered device that we're using to read out the state of the upper one. So the idea is that upper one is a card that initially has 110 units of value. Now this card is coming in, we're transferring money essentially to the other card. Again, all powered from the ambient TV signals. And now we're going to bring the reader back and read out the new value, which on the lower right is 130. So we successfully transferred message, and we also did some error checking and so forth. And now you'll see one of the applications we were thinking about. If you have the ability to put tags everywhere, you could use that for things like tracking objects in the environment. So maybe I have some of these tags built into my couch. Maybe there's one of the devices on the keys. Now when I leave the couch, because you've built this ambient intelligence everywhere, the couch is able to say, hey, you left your keys. So that's kind of the IoT vision, of course, is just putting intelligence everywhere. But if we can solve the power problem and the communication problem, then it becomes feasible to actually do that. Now, in the early examples that we had there, we were only able to transmit data a few feet. This year, in a follow-on paper at SIGCOM, we showed that using coding, we can make the range go up quite a bit, up to, let's say, 40 feet for some reasonable signal strength. And then the other really exciting follow-on that we did this year is showing that we can do this for Wi-Fi. So I'm not going to go into a lot of detail on this because Bryce Kellogg is giving a talk on this later. But the quick version of this is that we showed that we can communicate with a Wi-Fi access point in both directions by using these sorts of ideas. So one question is, what next? What to do with all this? It seems like it's now possible to wirelessly power and communicate with some significant sensors, cameras and microphones. So how can we really make this a reality and realize the promise of all this? So Sham and I and some of our students are starting a company that we're calling Jiva Wireless, and we're trying to do power and internet connectivity for the next billion devices. So we want to solve the battery problem and use Wi-Fi to power the Internet of Things. So we'll have what we call the Jiva router, which will provide ordinary Wi-Fi connectivity to your laptop and your phone and this sort of stuff, but it will also power these low-power devices and provide communication to those. So that's all I'm going to say about Jiva Wireless right now, but we're working on commercializing that. I'm very excited about it. So now I will tell you about some of the high-power, near-field wireless power work that we've been doing. So WRL stands for Wireless Resonant Energy Link. And this little video shows a Lanson sample, my first PhD student, in the first experiment where he powered a 60-watt light bulb. So the way that works is on the transmit side, there's a coil that's tuned. So it's tuned for one specific frequency. It resonates at that frequency. There's also a loop, which is inductively coupled to it. So we're not wired into the coil. On the receive side, there's also a high Q resonator, very carefully tuned, and then a loop. And there's actually a mechanical analog for a system like that. So the coil on each side is like a pendulum. So it has, a pendulum, of course, has a natural frequency that it likes to move at. The spring that you see there is analogous to the magnetic fields that link the transmit coil to the receive coil. So the entire wireless power system is like two coupled pendulums. And the thing about two coupled pendulums is they actually have two natural frequencies. One of the natural frequencies, the pendulums are going back and forth like you see on the left, and in the other one, they're going antiphase. And the frequencies of those are actually different. So the antiphase one on the right is actually faster than the one on the left. Now, what this has to do with wireless power is if we move the receiver closer or further from the transmitter, that corresponds to tightening that spring there, which corresponds to changing the frequencies, changing those two frequencies. So if we make a plot here, the vertical axis is the efficiency at which we can transfer wireless power. This axis is frequency, and this axis over here is distance. So basically, as we move the transmitter and receiver closer or further, the best frequency to use changes. So the nice thing about this is if we design a control system that keeps us on top of this V-shaped ridge, so as we move the transmitter and receiver back and forth or we change the orientation, if we compensate for that change by adjusting the frequency to keep us on top of this ridge, then basically we get constant power even as the transmitter and receiver move closer or further away. And when we first realized this was kind of surprising because, my intuition, and I think a lot of people's intuition, is that the further away the receiver is, the less power you're going to get. But what this shows is that in some regime, which we call the magic regime, if you do the control system correctly, you can move the receiver further away and you get the same amount of power instead of less power. Now, of course, that stops working eventually the further away you get. Once you're outside of this magic regime, it starts to fall off. But in this video, what you're going to see in the first part is we have no control system. So in some cases, when the light bulb is too far or too close, it's off. So there it's off. There's one sweet spot where it's on. Now in the next section of video, we're going to turn on the control system. And here you can also see that orientation affects it badly too. Okay, now the control system is on. So we can move that light bulb around quite a bit, and you'll see that it's just steady. It's not turning on and off because the control system is keeping us on top of that V-shaped ridge. And it works for orientation as well. And here's one other really neat trick you can do with this. You can actually make power multi-hop. So we put this coil in the middle, it's hopping into the middle coil and then on to the next one. So it's that coil in the middle is not powered. You can also turn the corner with it this way, which is kind of cool too. Okay, so now I'll tell you about one of the biggest applications we've been working on with this we call FREED, which is a collaboration with a heart surgeon at Yale named Dr. Pramod Bondi. So he works on mechanical circulatory support, so basically artificial hearts. Nowadays, when they put in an artificial heart, or at least this kind, they don't take out your old heart. They put it in parallel. And these are called left ventricular assist devices. It's essentially a pump that assists your failing heart. Now these pumps consume a lot of power. So this one consumes something like 20 watts. And so the only way to power these today is with a cord that actually protrudes from your abdomen. And you can imagine there are a number of problems with that. There's infection, sometimes they get yanked or pulled. I mean, if I went online once and started reading some of the emergency room doctors talking about bad things that have happened with these, and it's really scary. So what we want to do is implant this completely inside the person. Now here's a video of Ben wearing a transmit. It's just a transmitter, nothing's dangerous. And now he's going to pull out the receiver. Now this received part is the part that would be implanted inside in the real heart patient. I'm not sure why he didn't want to do that. But so you can see that at several inches from the transmitter, it's powered. And so this is initial proof of concept. Now the next video, if you're squeamish, don't look because you're going to see this implanted in a pig. So this is your chance to close your eyes if you don't want to see that. So that beating heart, there's an entire pig behind it. People have asked me. They don't necessarily understand that. But the transmit coil is here. The receive coil is under the pig's skin over here. This is our electronics that harvest the power. And the actual pump, in this case, is just out of the frame. So this tube is carrying blood one way through the pump and back the other way. So essentially, this works. We've implanted it in about 6 pigs successfully, and for this, we're working with the heart pump companies to try to get this out there. In terms of implanted electronics, we have a center here at the UW that Professor Raj Rao of CSE runs called the Center for Sensory Motor Neural Engineering. And we're also working on implanted brain sensors using these sorts of ideas. We also have a project with Chet Moritz and Adrian Fairhall of biophysics, funded by the Paul Allen Family Foundation, that's aimed at restoring motion for people who have spinal cord injuries. So the idea is if my spinal cord is cut so I can't control my limbs, we're going to sense the intention to move in the brain, and then we're going to stimulate in the spine below the place where it's cut. And the nice thing about that is it turns out the spinal cord is not just a wire, it's actually a computer. It generates a lot of the motion commands. So the nice thing is you can just put fairly simple commands into the spine, and it will kind of resolve it into the low-level motion control that you need to move. And so we're doing the wireless power and data for this project. We've also done some stuff in the near field range on wireless power for robotics. So we're working with Rob Wood at Harvard on trying to power his little robot bees, which you may have heard about. As an intermediate step, we've started with his robot cockroaches. So that robot is being powered by the coils underneath it. So we call this a wirelessly powered robot. And recently we've had a lot of interest, surprised us, from robotics companies in wirelessly charged robots. So this is a Silicon Valley startup that's working on a personal robot. That's our transmit coil on the right, and this is a demonstration receive coil. And you can see as the robot aligns with it, we're transferring power. So the key benefits of this are reliability. So getting these robots to line up properly is actually difficult, especially if it's not a super expensive robot. And those contacts wear and subject to maintenance and so forth. So we've had really a lot of surprising number of inquiries for this. So Ben Waters, my student who's just about to graduate, is starting a company that he's calling Wybotic to try to commercialize that. So if we step back and look at all of this stuff, you can imagine how it all comes together in things like the work that's going on at the Neural Engineering Center. We've got opportunities to sense inside the brain using things like the WISP. You can imagine a robot arm that maybe has various kinds of sensors in it and is recharged using the high power wireless charging that I just showed you. So all these things, I think, can eventually come together in really, really exciting ways. As far as today, I just want to advertise one of the sessions where a lot of this work is going to be talked about. So in session 4 at the end, Sham Galakota is organizing a session that has talks on zero-power Wi-Fi connectivity, transforming Wi-Fi into a camera, wireless battery-free camera, which I just talked about, and wirelessly charged robots, which I also just mentioned. So the research challenges that we're looking at in the future are continuing this energy efficiency scaling. That will make this all possible. Harvesters that work further away and with more efficiency. A lot of interesting networking questions that we're looking at, and RF power-aware protocol design. So ultimately, what we're trying to do, in the next few years is make sure that the Internet of Things is part of the real Internet, and make sure that the Internet of Things is not the Internet of dead batteries. So thank you very much.